Hello, welcome everybody. My name is Patrick Seid and I'm going to talk about FreeRTOS in this presentation. FreeRTOS is a free implementation of a real-time operating system and I'm going to show you in several examples how does it work. This presentation has several attachments. You can find these presentation slides, the notes for the slides, and several examples that are used inside the slides. I would like to recommend you to see the presentation slides and these notes first. Then, if you find something unclear, please follow the corresponding slides on this video presentation. You can find the video timing in the beginning of every slide in these notes. You can check the source codes of the corresponding example. The source code contains the command with the numbers of corresponding slides. If you still have any questions or if there is still something unclear, please contact me in the discussion forum inside information system or via email. You can find several examples that are using FreeRTOS implementation in ESP32 microcontroller. These examples show you the basic fundamentals of this FreeRTOS. In the end of this presentation, we will talk a little bit about concurrent data structures that are included inside FreeRTOS. This presentation doesn't include any details and theory about real-time operating systems, and we are not going to talk about any other real-time operating system than FreeRTOS. First, we are going to talk about the used hardware in general. Then we are going to build the minimal working example, and the main part of the presentation is dedicated to tasks and jobs. In the end, we will talk a little bit about sharing data among threads and the concurrent data structures. FreeRTOS can be compiled for several platforms. Some manufacturers already included support of the FreeRTOS in their own chips. For the other hardware, you have to port it and build the source code by yourself. Here in this presentation, we selected ESP32 microcontroller, which has the native RTOS support, and there is already implemented an Arduino application programming interface. We will use the Arduino API for building the examples and for blinking with light emitting diodes. Here the ESP32 is mounted on Arduino Learning Kit Starter, which is an electronic board for beginners and contains several basic peripherals like LEDs, buttons, potentiometers, speaker, sensors, or connectors. We will use the connected LEDs for visualization of the FreeRTOS task. You can see the running RTOS tasks directly as flashing diodes, but usually the diodes are flashing very fast, so we cannot detect the blinking by human eye. Because of this, we are using an oscilloscope inside this presentation. Here you can see the simulation of basic traffic lights. There are green, yellow and red LED, and we can see the behavior of these LEDs on the oscilloscope. Now the red is high, low, again high and again low. We can see the whole behavior on the graph. Now let's change the period of this periodic process by selecting the correct trigger, and now we will be able to see the whole period of this periodic process. Now the period is the same on the oscilloscope and on the running example, so we see almost no change on the display. Now we change the settings a little bit more and we can see the difference on the trigger. Now the example board is off and the LEDs are all off, so we can see no behavior. Now we made the traffic lights a little bit faster, and now it's on the edge of the human eye to see the LED behavior directly. Now in these fast processes, it's much better to see the visualization on the oscilloscope. Because with the oscilloscope we can zoom in the time and see the really fast processes on the display. The oscilloscope simply measures voltage with time. It displays a graph where x-axis is corresponding to the time and the y-axis is corresponding to the voltage. Here we can see the image captured by the oscilloscope in detail. We can see three lines, red, yellow and green, each corresponding to the LEDs on the simulated traffic lights. On the y-axis, again, you can see the voltage change. When the line is low, the LED is off, and when the line is up, it shows the voltage of 5 volts or 3 volts. You can see the LED is on. Here, the graph visualizes the periodic process of the traffic lights where the red, yellow and green lights are changing constantly and forever. Now we are going to talk a little bit about minimal working example. The minimal example consists of two functions, function setup and the function loop. You have to implement these two functions to be able to run any Arduino based project. The setup function is called in the beginning of the program directly after boot, and then the loop function repeats forever until we shut down the whole system. In the beginning, we have to tell to the processor what peripherals, what LEDs or buttons are connected to which pins of the processor. The pin mode function tells to the processor that there is a LED connected and the LED is an output device. For example, the button is an input device. Another functions, the function digital write, can set the value on the pin of the processor. So we can set the pin to high, to 3 volts, or low, to 0 voltage. When the voltage is set, the LED is on, and when we set it to low, to 0 voltage, the LED is off. The delay function simply waits for the specified number of milliseconds. But there's another type of delay, and this is the function of FreeRTOS, the wtask delay, which waits the number for the number of scheduler ticks. We will talk about it later. Here you can see the minimal working example inside Visual Studio Code with a Platform I/O plugin. The Arduino Learning Kit starter with ESP32 controller is connected via USB to the computer with the Visual Studio Code, and the program is uploaded directly from the computer via this USB connection. Now let's see the difference between different delay functions. The first one is a simple busy wait where the processor is inside a loop until the 1000 milliseconds last. And the second function gives a time to another thread, to another task. But this function waits for the number of real-time operating system ticks. So if we want to delay for a specified number of milliseconds, we have to divide this number by the number of milliseconds per one tick of the real-time operating system. Here in this example, the scheduler of the FreeRTOS is running at 1 kilohertz, so it means that one period of the scheduler is exactly 1 millisecond. So the constant porting period ms is equals to 1. You can see the detailed description of the delay functions inside the documentation of the free real-time operating system. I would like to tell you one thing about the naming convention inside this system. Let's see at the structure of each function name. There is a prefix v, u, l, s, etc., which defines the return type of this function. Now we can move to the main part of this presentation, to the chapter tasks and jobs. When we want to create a new task, we have to implement a function which is called inside the task, and then we have to specify a few another parameters, like the stack size, like the parameters given to the executed function, priority of the task, and if we want to handle this task in the future, we need to specify the task handler. For the future examples, let's imagine a function blinklet forever. This function does only one thing. It periodically switches on and off the specified LED, the specified light emitting diode. Let's see what happens if we define a yellow task which only calls the function that blinks the LED forever. Now let's see what happens if we create a yellow task which uses this blinklet forever function, and we will create and run these tasks in our example. We can see on the oscilloscope that the LED is blinking all the time, but there are some gaps. The gap lasts for 220 milliseconds, and we can see that the gaps are present periodically. The distance between two gaps is a little bit more than 5 seconds, but the program is running exactly 5 seconds between these two gaps occurs. In reality, these gaps are resets, internal resets of the processor. Why this happens? Because the processor is fully occupied by the yellow task and it has no other time for running the scheduler or the other tasks. So every task has to trigger the watchdog timer on time, and when the function missed the deadline for triggering this watchdog, the real-time operating system thinks that there is an error and it will reboot the whole microprocessor. When we create a new task, we have to keep in mind several things. When we are creating a new task, we have to keep in mind several things. The scheduler is running on the same CPU as our tasks, and we have to reserve some execution time for the scheduler and the other interrupts. The FreeRTOS has some watchdogs, and if the scheduler or the task doesn't trigger the watchdog on time, then the watchdog reboots the whole processor. The watchdogs can be disabled, but I don't recommend this because the task shouldn't occupy the whole CPU. Now we will add some delays into our task, and the delays will split the task into several jobs. Inside this delay, the CPU has a time to run the scheduler or reserve a space for another task. Now let's see what happens. We will create a red task with delay of 5 milliseconds between each LED toggle. Now we can see no interruptions on the oscilloscope, but when we zoom in, we can see that the LED is on exactly for 5 milliseconds and then it is off exactly for another 5 milliseconds. So please keep in mind that your tasks can be interrupted by the scheduler or by another interrupts that are enabled on your CPU. The context switching consumes time too. So it means that when one task is suspended and another task is executed, this suspension and execution takes a few CPU instructions too. The CPU can reset itself when the watchdog is enabled and when the watchdog is not triggered on time. And don't forget about the main task. It's another task running on your CPU. If you create two new tasks, there is still the third one, which is your main function. For example, the setup function or loop function inside these Arduino examples. Now imagine again the previous example and we will pin the yellow tasks to the CPU core number 1. The scheduler is running on the CPU core number 0 and we will disable the watchdog. Here you can see the implementation of the previous functions to remember them. When we want to pin a task to a specific core, we can call a function xTaskCreatePin to core instead a simple xTaskCreate. Here it looks that the task is running without any interruptions and we can't see any gaps on the oscilloscope. Let's zoom in again and we can see that the LED is on for exactly 130 nanoseconds and again for the same time it is off. It means that the CPU needs exactly 226 nanoseconds for execution of the whole loop. There are only two digital write functions inside this for loop and we can see how many CPU cycles we need for execution of this Arduino function. But when we zoom into another place, we can see a gap long 8.6 microseconds. There is no CPU reset like in the previous examples because the CPU reset takes much more than 8.6 microseconds like in this example. This gap occurs exactly every 1 millisecond. The scheduler tick rate in this example is at 1 kHz, so it means that the scheduler is executed every 1 millisecond too. So the gap here shows exactly when the task is suspended and when the scheduler is running. When we zoom into another place, we can see that the scheduler is running for a little bit different period of time during every execution. Here you can see the very zoomed detail and on the graph we can see the LED blinks and again the gap of 7 or 8 microseconds long. We have to keep in mind that the tasks can be interrupted by the scheduler and by another defined software or hardware interrupts. If we want to run an uninterrupted thread on the CPU core, then we can't use the real-time operating system on this CPU core. So let's move to the multiple tasks section. Here in this example, we use a dual core processor and we are going to define three different tasks: red task, yellow task, and green task. Obviously, the red task will control the red light emitting diode, the yellow one the yellow diode, and the green task will control the green diode. Red and yellow tasks are created by the xTaskCreate function, but the green tasks will be running inside the main function. Now let's see what happens. The red and green tasks are sharing the same CPU core, but the yellow task occupies the whole second CPU. All tasks have the same priority here, so it's up to the scheduler how it will handle this situation. Now let's change the priorities of the tasks. The red tasks will have the priority 2, yellow tasks will have priority 3, and the green tasks keeps its priority 1. Now let's see what's happened. The red and the yellow tasks will occupy the whole CPU, both CPU cores, and the green task has never been executed because the green task has the lowest priority. Now imagine a different situation. The red and the yellow tasks will have priority 0 and the green tasks will keep the priority 1. Now the green and red task occupies both CPU cores and the yellow task has never been executed. It's up to the scheduler if the red or the yellow task is executed or not. The red task is executed here because it was called the first. Now let's move to the next section about jobs. Imagine a function, a task, where there is a job running for the specified time in microseconds, and then there is specified a waiting time in milliseconds. This function simulates a set of jobs inside one task. Imagine that you have to periodically read some data from a sensor, for example. So you have to periodically execute a function that will read the data and then you can wait for another reading. Now we are going to talk about periodic tasks. We can see here that waiting for 1 milliseconds means waiting until the first scheduler tick occurs. So it can be a little bit lower than exactly 1 millisecond. But the waiting time is not guaranteed. You can see that directly after boot, the situation is a little bit different than in the previous example. Now let's change the execution time of each job to 900 microseconds and then wait again 1 milliseconds. We can see that the first scheduler tick is missed and the waiting function waits until the second one. Here the waiting time is a little bit more than 1 millisecond. Exactly it's 1100 microseconds. The similar change occurs directly after boot. Again, as in the previous example, this is not guaranteed. Here, directly after boot, the situation is again a little bit changed. When the execution time of the job is 1.5 milliseconds, we can see that the first scheduler tick is again missed. So what is the shortest time we need to reserve to not miss the first scheduler tick? Let's make a few examples here. Now the execution time is 1.5 milliseconds and the waiting time is exactly 1 millisecond. Here the execution time is exactly 1488 microseconds and the waiting time is 1 millisecond. We can see that the first scheduler tick is not missed here. When we add only 1 microsecond to the execution time, so now the execution time is 1489 microseconds. Now the first scheduler tick is sometimes missed and sometimes not. When we add 1 more microseconds to the execution time, we can see that the first scheduler tick is always missed. The best practice for handling the jobs inside the task is not by using delays, but it's better to do it by using timers. We will be talking about it a little bit later. Here, in the end of this section, try to think about a small exercise. Imagine 3 different tasks like specified on this example. The tasks have different priorities and different settings. Try to think about what happens and how the scheduler will handle this situation. You can see the result here. Let's see that sometimes the red tasks and the green tasks are executed at the same time, but during the different time, the yellow and the green tasks are executed at the same time. In this presentation, I've shown you several task control functions, but I didn't present all of them. If you are interested in more advanced functions, please refer the FreeRTOS documentation on their webpage. And now let's move to the last section of this chapter, timers. Timers are the best practice to handle jobs inside a periodic task, but in most hardware architectures we have a limited number of the hardware timers. But more tasks can be dependent on the same software or hardware timer. Please see the FreeRTOS documentation for more information about the supported application programming interface. For creating a new timer, we need to specify the period, if the timer is executed only once or if it is a periodic task. It's a good idea to create a timer ID for future control, and the most important one is a callback function, the function which is executed when the timer is triggered. Now imagine a blinklet once function which represents a job that lasts 1600 microseconds. The timer will execute this function every 2 milliseconds. We can see the result on the oscilloscope, and now we don't have to take care about any missed scheduler ticks, etc. The timer will handle all the timing of our job. Let's move to the final chapter of this presentation. This chapter is about sharing data among threads, and it is more about parallel systems in general. The real-time systems mostly work with more CPUs, so the theory of parallel system is important here too. I've selected only critical sections and queues because they are probably the first concurrent structures you will need in any of your implementations with FreeRTOS. But remember please that there are much more parallel data structures you can learn in other subjects. Here we are going to talk about critical sections. The critical section is a set of instructions between entering and leaving commands. The code inside the critical sections cannot be interrupted, and no other task can activate the same critical section handler when the first one is still running. For example, you can handle some memory writing and other shared resources using this parallel structure. Imagine a function with the critical section and the same function without it. The entering and leaving functions of the critical sections are displayed on line 6 and 8. You can see that they are commented in this example, but we are going to uncomment them later. Now imagine two tasks, red and yellow tasks, that are using the same function with the same critical section. Now we can use the same example where the red and yellow tasks are created and the green task is running inside the main thread. Now let's see what happens when we don't use the critical sections. Let's see that the yellow and the green tasks are executed at the same time. So when they share the same memory or the same resources, the problem will occur here. We can see that the situation periodically occurs, and almost always when the yellow task is running, the green task is running too. But when we enable the critical sections, now the situation is quite different. We can see here that the red task is executed as the first one, the yellow task as the second, and the green task as the last one. And if we move a little bit forward in time, we can see that the situation is the same and no shared memory, no shared resource is shared by two tasks in the same time. Finally, let's move to the last section of this presentation, the parallel queues. The parallel queues work in the producer-consumer layout. They are tasks that write, push something to the queue, they are producers, and there are another tasks that can read, get something from the queue. They are called consumers. You can define the maximum number of elements that can be stored in the queue. This is the queue size. For example, imagine one thread reading some data from a sensor and another thread processing and writing the measured data to the persistent memory. Then, the thread which is reading from the sensor is the producer. It writes the captured data to the queue. And the thread which is reading the data from the queue and processes them is the consumer, because it is reading the data from the queue. Then, the thread which is reading from the sensor is the producer. It writes the captured data to the queue. And the thread which is reading the data from the queue and processes them is the consumer. Now imagine an example with queues. The example shows 3 tasks, one producer, the green task, and 2 consumers, the red and the yellow task. The image on the oscilloscope shows when the task is writing the data, the green task, and when the other 2 tasks, red and yellow, are reading the stored data from the queue. Let's move again a little bit forward in time, and we can see how often the data are written to the memory by the green task and how often they are read from the memory by the red and the yellow task. You can check that the number of green jobs, the number of writes, is exactly the same than the number of reads, the number of red and yellow jobs. If we zoom the oscilloscope a little bit out, we can see this periodic process in more general view. Here you can see the log of all these tasks. The log shows when the green task published the data and when the red and yellow tasks read the data from the queue. You can see very similar examples in exercises dedicated to parallel and distributed systems in general. This example is a screen capture of the serial terminal connected to the Arduino Learning Kit starter with the ESP32 processor running with this example. Thank you for your attention in this long presentation. I hope you enjoyed it. And in case of any questions, please refer to the dedicated forum in our information system or write me directly to the email. So, have a nice day and thank you.